Hello, everyone, and welcome to today's webinar, Getting the Most Out of Your Data, Advanced EBSD Data Processing and Reporting in OIM Analysis 9. Before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We'll attempt to answer any questions for the speaker at the end of the presentation. If we don't get to your question, don't worry, we'll follow up via email after the webinar. Now I'd like to introduce the speaker for today's webinar. René Decloux has been working as an application specialist for EBSD and later also EDS at the EDAX European Support Office in Tilburg since 2001. His focus is on instrument demonstrations, conference and workshop presentations, and after-sales customer support. This includes on-site training courses, assistance with analytical problems, and scientific collaborations. Although focused on Europe, his work has brought him to customers and conferences all over the world. As he's always been fascinated by the physical world around him, René has chosen to study geology at Utrecht University with specialization in material science from a geological perspective. René's first introduction to electron microscopy and microanalysis came during his undergraduate thesis on deformation and pressure indicators in natural fault rocks from New Zealand, which involved a significant amount of SEM and TEM work. Later, during his PhD thesis on nanometer scale melt structures in upper mantle rocks, he also learned about high-resolution TEM imaging and EDS analysis. Around this time, he also started using EBSD on the system without any automation. René's background in geology gives him a slightly different view of material research, which has proven invaluable over the years at EDAX. In geology, one must often look at a material without any prior knowledge on how it was formed. Applying this view to man-made materials can be a great help in explaining unexpected test results or materials failures that customers need to understand. Now over to René.
Okay, thank you very much, Jonathan. Welcome everybody in the webinar. If you have any questions, you see on the screen here where you can enter the questions, and we will talk about those at the end of the webinar. Okay, so getting the most out of your data, advanced EBSD data processing and reporting. What am I going to talk about here? I really want to introduce OIM Analysis 9. If you have used OIM Analysis before, a lot will look familiar, but I'm sure you will find some features that you may not have found yet. And I will start with finding your way in the software. Then getting quick results, full flexibility, of course, it's important. Then repeatability, data selection, and what can we do about reporting? Now, the quick results is what I call the standard analysis, or in the software, it's the quick generate toolbar, predefined analysis. Then for the flexibility, everything you do, you can customize. You can right-click on different displays. You can select what you want to do. You can make any changes. Then when you want to redo an analysis that you have done before, or you have a sequence of experiments that you need to analyze the exact same way, we can repeatability, we can make templates. So you can just repeat whatever you've done over and over again with the same results. And then the data selection. This is actually one of the core functions of OIM analysis. We call it partitioning, and I will spend quite some time on that in a moment. And then finally, reporting. Yes, of course, reporting is included. So, but let's start with the basis. When people start talking about EBSD, it's almost always starts with the detector. How fast is your detector? How sensitive is the detector? What can you do? And of course, that is crucial. So if you have an EBSD detector, a system, here's just a quick indication of what the Apex software looks like, collecting an image, do a camera setup, and then collect the data. So while we're doing this, you can see this is running now close to 5,000 points a second. It's a dual phase material. And we get nice images. And while this is running, we can switch to a few different displays. For example, there's the phase distribution. This is austenite versus ferrite. We can tell it apart, and then the scan is done. And that, of course, is where it all starts. Because at the end of the day, we're not talking about the EBSD system that we have used to collect the data. At the end of the day, it's your sample, your microstructural description that is important. And for that, we have orientation imaging microscopy. So in a microscope, we use electrons to create pictures to understand and visualize our microstructure. With EBSD, after we have collected the EBSD data, we can use the orientation outcome of the initial map to create pictures. So that's why we say orientation imaging microscopy. So we look in detail at your sample, but based on the orientations and no longer on the electron signal. And we do that with the OIM analysis software. And the software is written for the visualization, quantification of microstructural data. And it's used for visualizations. So we can create the maps, the colorful images that everybody is used to with EBSD. We can quantify those in charts. Then we can look at discrete plots, so just showing all the orientations according to different definitions. We can quantify those as well in texture calculations. And finally, when you need the raw data or any calculations that are done in the software for external programs for additional work, you can export data and get a plain text file, and you can do your own work. Now, this is what the software looks like. If you've used the software before, you'll notice that the toolbars look a bit different. We have on the top of the screen here, we have a ribbon bar. And in the ribbon bar, we have combined the different toolbars. We combined all the functions. And the most important ones for now is this section here, the quick gen section. This is where the standard analysis are predefined. You can select image quality, IPF maps, grain, cam. When there's a little arrow next to it, you have a pull down. You can automatically get an overlay on top of an image quality map, for example, so to get a good display. And then here on the right-hand side, we have the highlighting section. That's the interactive analysis. Then here at the below it, we have a custom toolbar. If there are certain functions that you use very often, you can just drag and drop almost from here. It's right click and add to toolbar. You can make your own custom toolbar, so you have the functions you need always at your fingertips. Then on the left, the project tree, and I'll go into a lot more detail about that in a moment. But that is where all the data, all the definitions of what you're doing are being displayed. And then in the large area, we have the results. We have main views, so maps and charts and plots and some text windows. And next to that, you may have a secondary view with a legend or some other display functions. Okay, now the most important thing when you start working with OIM analysis is this organization. The analyses are organized by partition. And what do I mean by that? If I zoom into the project tree, you can see there you have different levels. And the project, that's the root level. Everything you do goes in one project, in one file. But in that project, we have these data sets, those black icons. And I always describe those as bucket with numbers. That's where the data is, nowhere else. So your XY coordinates, your orientations, image quality values, detector signal, everything is in there. And underneath those, we have partitions, the red icons that you see. And a partition is a filter, which points to take from the bucket. So if you say, I have a partition that's called all data, not much of a filter, we use everything, but you can make your filter here. So this is in a dual phase titanium data set. I have alpha titanium grains, but only the small ones. And then you can do your analysis on that, or all alpha grains, and so on. You can change whatever you want in these partitions. Then inside the partition, you can do your analysis. You can make maps, you can make charts, you can make texture calculations. Inside a partition, you can have multiple with different definitions if you want to. And inside a texture, you have your texture displays, the texture plots, ODFs, pull figures, etc. I'm going too fast. So in there, what is important to realize is that when you make an analysis inside a partition, the maps or textures or plots will only use the data that you allow in that partition, in that subset. And we'll get to that further on. Then in the end, when you want to compare data from different data sets or different partitions, you cannot make a display in a partition because that would only show the data in there. You can make a multi-chart in the root level. And in there, you can combine information from different partitions or different data sets. So that is the layout of the project tree. Okay, once we have that, let's take a look at the toolbar, at the ribbon bar. Here we have the quick generate section. So if I want a quick display of my map, I just hit the button, IQ, I get an image quality map or an IPF map or any charts. So these charts are predefined and those give you a very quick startup for your analysis. However, when this is not what you're after, you can change them. And changing them is through contextual menus. Everywhere in the software where you think, oh, I would like to make a change, just right click and you will find the tools that you need to make that change. And for example, I want to change this map. I right click on the map, go to the properties of it, and I can change a grayscale map. I can add a color coded map. There's a long list, but let's add an inverse pull figure. Just add that, hit OK, and you can see here now we have the combined map. And this way you can modify any display. It's a very consistent mouse click sequence. With that, you can make any combination. So the map here on the right is an IQ map in the background with an IPF map on top with different boundaries defined on top of that. And here I have the legend. Those are just high angle boundaries and two twin type boundaries, sigma 3, sigma 9. When you need to use this map more often, you can of course make it all over again every single time, but that's not very practical. And for that, we can save those analysis definitions as templates. So you only have to generate your display definition once, save it as a template, and you can use it over and over again. And you can make templates for maps, plots, charts, textures, and even full analysis. So if I have a data set, I can have multiple partitions for all data, phase 1, phase 2, phase 3. Inside each of those, I can make the analysis I want to see for that. And I can save everything in one go in a template. And once I've done that, I can batch process the data. So again, when I have a sequence of data sets that I need to analyze the same way, I do the analysis once, save a template, and put it in a batch processor. That allows me to do all the analysis automatically and also saves all the images with one mouse click. And if required, you can export all the data as text files. Okay, now why are these templates so important? Just as an example here, a lot of the EBSD maps have what I call a fractional color coding. The scaling in a map goes from minimum to maximum of the data that is displayed in that map, and that's the color range. So here we see the minimum is blue, maximum is red. But if maps are collected on different samples or at different magnifications, this can give a very misleading structure, misleading interpretation, because here it looks, yeah, red grains here, red grains there, red grains there. They look similar, so it's probably okay. But when I look at the scale bar, which I took off on purpose, so you can see this is the scaling of the grain size in these maps. So here the 3.1 is red, Here 6.1 micron is red, and here 10.2 micron is red. So comparing the data, the grain size distributions by color is really hard. So what you would need to do for an honest comparison is look at the scaling for the largest setting, set up a template there, fix the scale, and then you can display all your maps in the same color coding. So now we have a very clear visual representation of those grain structures, and we can actually see an evolution in the microstructure. So that's one of the uses of templates. Now, once you've made these templates, we can stick them in a toolbar. So I just showed the IQ map and the IPF map and the charts. Well, in addition to that, we have some places in the toolbar, in the ribbon bar, I should say, where we can define our own templates for maps, plots, charts, partitions, data sets. So all the levels in the project, you can predefine and put them here. When you have more, there's pull downs and you can just select multiple ones. But the most common ones you can directly program into the ribbon. These templates can then be used for batch processing, as I mentioned. So there's the batch processor. You can do some general applications. You can do a cleaning if you want to. Please be very careful with that. Don't do it too much. You can do a rotation. But the most important thing here is you can do a template. You do the analysis automatically, and then you can export images as you wish. You can export the data in different ways. You can export the as images, as text file, etc. Okay, so far for the general operation of the software. So those are the maps, the plots, the charts, the templates we can make. Back to the partitions, because as I mentioned, the partitions is what defines for us what data we want to use for analysis. And if I go to a partition and I right click there, I can open the setup window. And here I can define what properties a point or a grain has to have before I allow it in my partition. And one of the first analysis I always do is a filter to remove bad points. In the past, we used a confidence index filter up here. But in OIM 9.1, there's some new functions here, and one of them is maximum CI. And what that does is, I've set it up here, I say a maximum CI above 0.2. What it means is if I look at my confidence index chart, when I have a CI of 0.2 or higher, effectively everything is okay, everything is well indexed. And in the past, if I used the CI filter, I would just get from 0.2 and higher. I would use all the data that has a higher value than this. And then I could use a CI standardization to include some more points. What we've done here is change it for a grain max CI. And what that means is that I look in a grain, I find the pixel with the highest confidence index value, that's the best indexing solution. And all the points with the same orientation are automatically selected without having to do a standardization, which as we did in the past. So what that means is that effectively all the points below the curve, even if the CI is 0, as long as the orientation fits the grain, we say, okay, we want to use it. Again, it's really important to remember, a partition doesn't change data, it only selects it. So when I make a confidence index filter, I'm not changing my measurements. I'm only choosing which points I want to use. So with a grain max confidence, I just select to use all the points that are properly identified with an orientation to match all the grains that I have in my data set. And as an example, I have here a pole figure. This is the raw data, no filter. And after this filtering, I only have this. And you can see that all the noise has disappeared. Another use of partitions is to select a certain part of the microstructure. And In the screenshot before, I showed you that we can look at alpha titanium grains with a certain grain size. This is where you do that. So you look for the phase, that's for a pixel. And then for the grain, you can set a size or in points or in the diameter. There's your grain definition. You say, okay, it has to be smaller than 2.5 micron. And then only the grains in your data set that were identified as alpha titanium and have a smaller size than 2.5 micron will be allowed in your partition. You can display them here in color on a gray level background. And if you make a pole figure, it will only show those points. If I look for the larger grains, I just flip this operator to larger than 2.5. I get the big ones. And I can this way separate small grains from the large grains, looking at the pole figure distribution or a texture, if that would be relevant. A automatic partition application is the phase separation. So we do that during mapping in the indexing algorithms. If I have a multi-phase sample, a duplex steel, or here I have ferrite, austenite, there's some small ferrite particles left over here. During indexing, the software recognizes what's what, and it automatically tells them apart. So I get, when I open that data set, I get a partition just for austenite, just for ferrite, and I can use that, because if I don't do that and I make a grain size distribution, the software will just use all the grains in my data set. And this is my grain size distribution, fine. Then the average here is about 8 or 9 micron. But if I do that for the individual phases, you can see a big change. So the red one is the same as on the left, but blue and green are split between the two phases. So I have very small ferrite grains, which are on average about 700 nanometer. And then I have my large austenite grains, which are close to 9 or 10 micron. And when I separate them, I can also look at misorientations between the phases. So instead of looking at all the misorientations through my entire data set, I just select, okay, phase 1, phase 2, how do they interact with each other? And in this case, it's a very sharp misorientation distribution indicating the phase transformation relationship between these two. That was based on automatic selection. It's not always possible, depending on what you want to do. But here, for example, I have a partially recrystallized steel, and I would like to separate the recrystallized grains from the deformed ones. One parameter that you can use for that is the grain orientation spread. That's the overall gradient of orientations in a grain. A recrystallized grain has very small spread, a deformed grain has a large spread. So when I look at in a chart, so I can quantify that here, I can just select everything below 1 degree and say, okay, that's recrystallized, and I can separate that, and deformed fraction here on the right, that's the rest. And then again, you can tell them apart, and you can look at any specific analysis that you may want to do for this. That was using what we call highlighting. So I can select a section on a chart. Now, if I go here, I can also do it interactively. This is a gold silicon die attach on silicon substrate, power transistor application, so pretty heavy duty material. And I have a very nice IPF map. I can see large grains. I have some small grains here. The Prius map here on the right shows that structure very nicely as well. Question is, how different are those grain size ranges? So what I can do, I can just set a tolerance, and I say, I click in the map and I select the big grains, just visually, I select them myself. So these are the big ones. And then I can tell these two apart. So once I've done that, now I can do the analysis. And for example, I can look at low angle boundaries in there. And obviously, as expected, the number of boundaries in the fine grain structure is much higher than in the coarse grained fraction. So that's a vertical number scale. But I can change that. I can also look at the fraction. And when I do that, you can see that the distribution is identical between the two. So there's not really a change from the small grain to a large grain fraction. It's just a continuous range over this entire material, small to large, and the distribution in the misorientations just evolves with it and doesn't really change with the size. That is based on data that I have in my map. Now, sometimes I may want to separate phases that I cannot separate by EBSD alone. I could use EDS in some cases, also not always, but there is a possibility to do partitioning using what we call correlative microscopy. And what that means is that I can collect an EBSD map, and on the same area, I can collect data with another technique. That can be WDS, AFM, CL, Raman, after color etching, for example, an optical image, as long as it's from the same area. Then the software allows you to correlate those points. You can see some colored dots here of points that match the same area. Then there may be a little bit of an image skewing transformation to make it fit as good as possible. And then we can embed that information into the EBSD dataset. So when I do that here, it's superimposed. So there's my external map. In this case, it was a WDS map with very low concentration silicon in these phases. There is my quantitative chart of this distribution. And what I can do now, if I want to select those grains, because in this example, they had the same structure as the matrix, I can just select the bright areas. And now I have those identified in my map. And then I can tell them apart and do any separate analysis. And this will also work if you have a color etching for different steel variants, for example, as long as the area is the same. So you can use that to partition and divide your data set. Okay, now so far for good data. Now, if you have collected EBSD data, there will always be points that refuse to index for whatever reason. It can be pattern overlaps at grain boundaries, there can be dirt particles, there can be pores, there can be phases in there that don't produce any patterns, etc. But we can actually still use those. So as an example of that, I have here a 3D printed steel sample with some porosity. And what we normally would do is use the confidence index to remove these misindexed points. So if I do that, you can see here I've got some small white dots and they were speckled here. It's hard to see, but this is just the clean matrix and I've taken all the pores out. Great, I can use that. Now I can analyze my printed structure. But I can also use these clusters of misidentified pixels and call them anti-grains, by lack of a better name, because it's not always a pore. It can be a phase, can be any other reason why it doesn't index. But in this case, it's anti-grains. And I just flip my CI filter. I say, okay, show me the bad ones. And once I have that, you have these little dots, these clusters of bad points, and I can analyze those as if they are grains. Obviously no orientation, but all the morphology information can be analyzed. So here I have a size distribution of my pores. I can quantify those, I can highlight them so you can see where the grain size or the pore size is. And I can also do that with shapes. So I have here an aspect ratio, but there's all kinds of morphology information you can extract from areas that refuse to index. And in this case, the pores would have a good reason not to do that because there is nothing there, but we can still use that to quantify and describe our microstructure. Now, another very strong point for EBSD is that we know exactly where the data comes from. The point or the source point for each pixel is very small, maximum few tens of nanometers, sometimes even smaller. And in a map, we know where that is. So this positional information is crucial, and we can use that to correlate the data. We have this direct access, so we can just pull out individual points We can do all kinds of data manipulation or partition or subset generation. And I have some examples for that, what OIM analysis allows you to do. And the first one here is correlation by highlighting. So here I have, again, a recrystallized steel sample, an IQ map. By eye, we can recognize where the recrystallized grains are. Those are those larger, nicely smooth grains. And in between these areas with a lot of substructure, that's deformed. If I make a pole figure, an inverse pole figure plot for that, you can see that I have some dots. These probably correspond to the recrystallized grains, and these very large black areas that are caused by the deformation. So if I have lattice bending, this orientation just spreads out over a large area. But you can't see if you have any orientations for those recrystallized grains in those dark fields. Or can you? So if I go here now, I color code this map. I make it a grain orientation spread as I showed before. So we can look at low orientation spread, recrystallized, and a large orientation spread is deformed. I can then tell the software to use that data in my pole figures as well. So right click, and in the menu that pops up, you can say apply colors as highlight. And when I do that, it will superimpose the color coding for each pixel to those pole figures. And now you get a very clean separation of the recrystallized grains and the deformed grains in your pole figure as well. So if the recrystallized grains would have a preferred orientation somewhere, now you can see it. And in this image, you would not be able to see that. Another type of correlation, this is a laser crystallized silicon germanium film. So you see the traces of the laser crystallization, and a lot of the grains are elongated in this crystallization direction, but there's also quite a lot of these very small ones. It's hard to see. Now, of interest is this grain elongation, is that crystallographically controlled? Here at the bottom, we have a standard IPF map. That's the lattice plane of the crystals in the sample surface, or the plane normal sticking out towards us. So red would be 001, blue 111, and green 101. So it's a little bit of everything here. I could rotate that viewing axis and look at it from the top, but those planes are slightly oblique. And you can also see a lot of those smaller grains are not perfectly vertical. They are skewed inside each trail. So what you can do is first calculate the aspect ratio, identify grain ellipses. So here for each grain, we look at the longest axis, the shortest axis, we draw an ellipse around it. And then we can identify the crystal direction in the plane of the map along the longest axis of that ellipse. Now, this is a surface film, so that's easy, but you also have, when you make your own sectioning, you have to be careful with the sectioning direction, because the crystal direction we're going to see is in the plane of the sample. So be careful if you need to make a section through some structure. And then I can color code that. And here you can see that almost all the grains and have the a red direction, so the C-axis, very close to the longest axis of the grain. That's for the big ones. The smaller ones have all kinds of intermediate colors, so that doesn't really matter, but the big ones are all parallel. So there's a different type of information, and the reference axis for each grain is different. It's based on these ellipses that you can see here. And we can also use those ellipses for further analysis. So I can look at what we call the grain shape orientation. So I have my ellipse, look at the longest axis, and see what angle does that make with the horizontal. And that's what this color coding here indicates. And there's my chart to quantify it. So most are at straight angles to horizontal, so it's almost vertical in this map, as you can see. And you can color code that. You can make custom color codings. In this case, I made almost horizontal on both directions, blue, and vertical, red. So it's a symmetric color coding. And you can see here, red, that's just going along the crystallization direction, and blue is horizontal, perpendicular to it. And those there are quite a few of them, but they are much smaller than the other ones. So this is one way to quantify that. And you can display that in a rows diagram, for example, if the bar chart is not clear enough. Another relatively new function in the software is correlative plots. So when we do that, we can look at a certain property. Here again, I have my ellipses. There's my distribution of the aspect ratio. Most here is about 0.5, so not round, but not extremely elongated. And here's my grain size distribution. Now, what could be of interest, for example, is my elongation a function of grain size or not? Is there a certain directionality to this? And then you can plot those against each other. So if I do that here, I'm plotting the aspect ratio against the grain size. And then you can just see that the larger the grain, the lower the aspect ratio, so the more elongated the grain is. So that's a nice way to quantify that part of the microstructure directly in OIM analysis. If you need more information, more analysis on the data, you can always right-click on the map, export data, and you will get a text file with all the numbers that were used to create this display. Okay, and that's what I mentioned here. If you still can't do what you need, you can use your EBSD data as a starting point, right-click, and export your data. There's different types, grain information, boundary information, triple points, partition data, map values. So there's lots of things you can export in text files that you can process yourself afterwards. And I have here an example. This is an EBSD map of aluminium kitchen foil. That's a beautiful material. Just take the shiny side, put it in the microscope, and it gives nice EBSD results. We have this very strong elongation from the rolling of the foil. This is the grain size distribution. In this one, it's about 4 or 5 micron on average. And I can export a grain file. And in there are a lot of morphology parameters that I can select. In this case, I wanted to look at the number of neighbors. So that is a parameter that shows you the maturity of the microstructure. So the number of neighboring grains for each grain. So this is what that text file, that export looks like. And then I can just plot that in an external program. And most grains have 5 or 6 neighbors, as you can see here. So if you would anneal a structure, this distribution will most likely change. And you can use that again to describe the evolution of a material. And you can do this with many, many more parameters. Okay, now we've seen the partitioning, we've seen how we make the quick generate maps, we make templates, we can make our own analysis, and now we can use that also for reporting. So once we have created the templates, we can put them here in the ribbon bar. We can use that for a report. And when you install the software, there are some generic reports included with the installation, like a basic review, just an IPF and an IQ map, or maybe a grain size chart. Those are included by default, but of course you can create your own. So anything you like, any definition you've made, you can generate. And then we can create reports that automatically export all your images with legends if required, the charts, etc. So this is the default one, but we can do much more. We've seen that with the templates for the analysis. So what you can do is you can make your own template. You use your filter, you make your maps the way you want, you make your pole figures, your plots, any textures, anything the way you need it. Save that as a template. Then we go to the report designer, put your report together, showing the different displays the way you need, and save that as a reporting template. And once you've done that, you can just click on the report. You can program some of those in the user interface here in the ribbon. Automatically, all the analysis that was defined are generated. And when I'm happy with that, I say, okay, then that is dumped into a report that you have specified before. So with all the display definitions that you have made. And this is also possible directly from Apex. And this is specifically designed for facilities, maybe an industrial environment, where you have to do a lot of repetitive analysis. Then you can directly from the analysis here send to report. Now, what does that do? If I'm in the Apex acquisition, I make a template for my analysis. I prepare the layout for the report. And then I can select here, send to report, and load that template. So some analyst can make these templates, and then any operator, when they select that template here in the UI, will get the exact same analysis definition. So it doesn't matter anymore who is using the system, you will always get the same plots and charts for comparison. So when you collect the EBSD data here, when the mapping finishes, it's in the background automatically sent to OIM Analysis, and it applies a template, runs through all the calculations, and then the report pops up in the definition that you have specified. Okay. Now, that is the, let's say, traditional use for OIM Analysis with all the capabilities of the partitioning, the templates, the reporting. Not too long ago, a few years now, we have added a new dimension to analysis when we save the EBSD patterns. So in the past, we didn't always do that, but now we can use that and we can extract the patterns from all the individual pixels in the maps, and we can use that to optimize our indexing results. So one of the secondary view panes to a map, you can see here, I have flexi view. I can just look at my pattern, orientation, pole figure, a reconstructed pattern. I can just move my mouse and see all the data. That's just for visualization. But I can extract those points as well. Then I can modify the background processing if I need to. I can make a background specific for a phase. If you've ever made an EBSD map with multiple phases with very different backscatter coefficient, you know that it's not always easy to get a good pattern or a good background for all phases at the same time. This allows you to really tune a background for each phase, especially when it's really hard to separate from others. And this then uses only the patterns from the same phase. So it gets the optimum background processing. Finally, you can also do NPAR. So pattern averaging, for each point we take a ring of 6 around it, average those together to maximize the signal to noise if the patterns are really faint. And I have an example of that analysis, what you can do. So here I have a zinc aluminium alloy, and this is almost a story of my life. These are the samples I get with very little description. So zinc aluminium alloy, it's supposedly all the same phase. So I map it, and you can see the polishing was not ideal. There's a lot of noise in there. And can I use these stored EBSD patterns to make it look better? So what I do, normally we use a CI filter to select the good points. So if I do that here, I have about 75% indexing success and all the noise drops out. Great. I want to keep those points. I don't want to change them anymore. Those are good. But I can now flip that filter around and only look at the bad ones. And they didn't index for some reason, maybe the patterns were weak. But let's see if we can maximize the results. So when I go there, I can now tell the system, make a new background based on this partition only. So only use the patterns from these pixels and average those together for a background and use a subtraction or division based on those alone. Then, if required, I can enable NPAR to try to maximize the pattern quality. And in this case, while I was doing this, I recognized that there was actually pure aluminium in the data set as well. So I add a phase, and then I just re-index only the bad points. And when I do that, they are indexed as aluminium or zinc. And in this case, that allows me to increase my indexing success from about 75 to about 97%. So using these patterns and doing some reprocessing by optimizing the patterns with the background, NPAR, adding phases if you missed something, can really help you salvage poor data. And the same way we can use chemistry. So if you have a multi-phase sample with lots of phases in it, I always strongly recommend that you collect EDS data as well. That allows you to differentiate phases that are very similar, like copper and nickel, that will give almost identical diffraction patterns. Without chemistry, you cannot tell these apart. But it also allows successful indexing where the phases have very strong difference in pattern quality. With indexing or with polishing, some phases will polish really well, give beautiful patterns. Other phases may not polish as well under the same conditions and give very poor patterns. And when you then try to fit every phase to all the pixels, you will get a lot of misindexing in those phases. And you can use EDS to improve that. That allows for efficient indexing of multi-phase samples. And I have here an iron silicide with rare earth elements in it. And here I have some of the EDS maps collected simultaneous. And you can see by the intensity of the silicon, the iron, where the different phases are. You can use highlighting to say, okay, here I have FeSi, here I have FeSi2, here I have some cerium, lanthanum phase, whatever. And then you can just reprocess that, and you can use the chemistry to teach the software where each phase is sitting. And then in this example, I've got 8 phases analyzed, and I've got a really nice phase distribution for my further analysis. That's used for the EDS. But when we have the EBSD patterns, we can go one step further, because in this example, after collecting the data, I found some areas where the image quality was bright, meaning I have patterns, but it's noisy, meaning it didn't index. And when it doesn't index, it just means that I didn't have the proper structure. So let's try. So I use the chemistry now to extract those points, get a pattern. That's difficult when you have no idea what it is. So let's see if we can improve that. So we have some tools now to just select NPAR. We can make a new background processing. We can stretch the contrast. And now we can see the band distribution very nicely. And when we look a little bit more closely, this identifies as an orthorhombic titanium iron silicide phase. So there was a little bit of titanium in the structure as well, which I did not recognize in the beginning. Once you know what it is, you can just apply it only to the points that we have extracted here. So you don't have to rescan the whole scan. And now we get a beautiful grain identification of those grains. We merge them into the original map and you're done. So you don't have to recalculate everything when just one phase is missing. A quick comment on EDS. EDS data comes from a much larger interaction volume as EBSD data. So if you have small grains, your EDS information comes from a larger area. So there's a mismatch in the positioning when you use the chemical data. So here I have an IQ map of a nickel alloy with chromium carbides. And here on the right-hand side is the chromium map. And if I zoom in, you can see what I mean, that here we have in yellow the grain boundaries, but my EDS information is too big. It is outside of the particles. So if I want to use the chemistry to select the phases, I would assign the wrong phase in here the carbide in the nickel matrix, because the chemistry just extends in there. What you can do there, and you can just see what that means. So here we have this green area bleeding out of those small particles. What you can do in OIM analysis, we go to the data set, right click, clean up, and we can average the EDS data. That doesn't change any orientations, but we can average it by grain. And when you do that, we are forcing the chemistry to have a sharp change right at the crystallographically defined boundary. And now we have a very sharp phase separation. And this works really well down to grains of, let's say, 200-300 nanometers in size, when the EDS would be a lot bigger, but you can cleanly separate them in here. So that's just a little bit of a sideshow. Then we have had a few other webinars about this over the last months, but I just briefly want to highlight that with the reprocessing capabilities in OIM analysis, we also have spherical indexing in there now. So the conventional indexing uses the band detection and then the Huff transform, the triplet voting that we do to identify the orientation. With spherical indexing, we are using dynamical simulations, and we create what we call a master pattern. So this master pattern shows all the diffraction intensities that you can get in all directions on a sphere. And what we then do is we take the experimental pattern from the detector, we remove the projection distortion, and we fit it against that sphere and see where it fits best. And that allows us to identify the orientation. Now, when you do that, because we are using the whole pattern, it's extremely sensitive to small differences in EBSD patterns. So a 1% tetragonality is visible. We can separate those. So, and small changes inside bands are also visible. So phase separation, pseudosymmetry discrimination can be done when you have saved your patterns during mapping. Offline, you have a lot of flexibility in playing with this. There's no discrete orientation steps. We can get very high orientation precision. And it's also sensitive to broken up EBSD information. So if I go here, no need to detect individual bands. I just use fragmented information, a zone axis here, a bit of a band there is enough. And just to illustrate what that looks like. So here I have my maps, very noisy maps. And if you look at the patterns that I'm going to get, this is my flexi view in the secondary view pane. There are my patterns. You can see they are extremely weak. Now, in this case, that was on purpose. We just added noise to them. So we know the orientation of the original map. We know what it should be. So we have a reference point. And here we have nickel. We add a nickel simulation. There is my spherical indexing display, and there is my dynamical simulation. Here's another pattern. Index that. That's the simulation. And if you want to see how close it fits, you can merge the simulation with the original pattern and see if it correlates. Once you're happy with that, you can just run it. And as you can see with the same patterns, by eye, it's almost impossible to see patterns in there, but the indexing works very, very well. Now, skip that. We talked about NPAR. Here I have a little bit better example of what NPAR allows you to do. I have got a part of a data set with very poor patterns. But the bands are the same in all of those patterns, but the background noise is random. So the moment I start averaging some of these patterns together, the background noise cancels out, but the bands are still there. They will become more visible. And this is the actual pattern that is generated from those 7. So based on this central point here. And that is easily indexable. So here I have an example of an extremely deformed material, shot peen titanium alloy. The Huff indexing, when it goes dark, we're in trouble. You can see there's a lot of noise here, and it just doesn't index close to the surface where the deformation is, where we want to see the results. If I do this with NPAR and spherical combined, I can actually see the grain structure all the way to the surface. And we can zoom in here. All the data is visible, so we can investigate the microstructure. And if I zoom in, You can nicely see the small grains all the way here on the top. The vertical scale of this map is about 3.5 micron. So those grains are a few hundred nanometer. And there's the orientation. And here's the phase separation. We can actually trace the beta titanium lamella that are going through this shot peen surface all the way to the surface. So that is something that with the Huff indexing just was not possible. But when you save the patterns, run it through spherical indexing, we can do it. And here's just a few more examples. Here is a mineral, biomineral. We couldn't use high current. We couldn't use a longer exposure. And the indexing initially was pretty bad. But when we run this, you get a full representation of the microstructure. Not only the area that already worked somewhat, but even here where there was nothing. And now we have a full representation of the structure. Another benefit of the spherical indexing, I mentioned the pseudosymmetry. It is also really good for the orientation precision because it is not sensitive to overlapping patterns. So here on the left-hand side, this is conventional indexing, on the right spherical. This looks very similar, but when I look at orientation variations, this is a CAM map, there is a huge difference between the two. Here on the right-hand side, we have a very clean display of substructure, which is just a little bit lost in the noise here on the left. And when I take a profile, just pull it out. This is about, I try to draw it on exactly the same trace, and you can see the noise level in the image here. And here there's very little noise. If I blow up that, you can see here that the noise is well below 0.1 degree. So around 0.05, and here it is 0.2 to 0.3 degrees. So that's another benefit. When you save the patterns, you have the full flexibility for a lot more detailed analysis afterwards. Okay, now all of that was showing what OIM analysis can do. I would like to finish the webinar with a little case study. This is something that is quite typical for my work here. I get a sample, I know nothing about it, and I don't know the history. I just need to identify the microstructure and from the material identify what happened. And here I have a sample of stud welding. So it's a cross-section through a stud where a threaded rod was welded onto a ferritic steel substrate. For the method, what happens? We have the stud, we apply some electricity, we get an arc, it gets hot, it melts, we plunge the rod into the substrate, and then it cools down. This happens in a few tenths of milliseconds. It's very, very fast. And this is what the sample looked like. So mounted, 3 centimeter mount, this is the whole area here at the ferrite substrate. This is a montage map in the SEM. So we can recognize the stud itself and the substrate. And here's an EBSD map, a Prius image, scale 4 millimeter, 45 million points. So this was quite a big data set, but we can beautifully see the microstructure. This is a Prius image, so that shows orientation contrast. And here we have an IQ map, and this shows more information. Here we have image quality at the bottom. It's nice and bright. This is the undistorted ferritic substrate. And here we have the austenitic steel stud. Here we have the heat affected zone of the welding. And those big swirls here is what was molten. And then we have a very dark area underneath. So if I just pull that out and just look at the phase distribution, we have at the bottom still it's ferrite all the way to that interface, and then on top it's austenite. And here in the melt phase, this swirl as I call it, we have a little bit of a mixture of both. Now, what are we looking at? There's the original stud, recrystallized austenite. I have some columnar austenite. There's columnar ferrite, very small grain ferrite, and there's a substrate, and then on both sides I have a melt pool. Now, what have we here? There's the EBSD map. So we can see the structure. And first of all, the dark area is caused by deformation. So it's very weak patterns compared to everything else. And this is caused by the welding, by the heating and then subsequent cooling. If I look at area 1 here, this is the melt bubble that happened on the side. There was no prior structure. So very large grains are growing, and you can see these columnar grains growing from both sides effectively. Nice quality patterns too. And if we look at number 2, fine grain structure, just a recrystallized austenite. The whole structure relaxes, but the grain growth is not significant because it's so fast and it cools down very quickly. Now, if we look a little bit closer to the center, we have columns, a thin layer of columns, and then we have columns going into the ferritic base. And you can see which area was affected by the weld. So if we zoom into this, we clearly have different regions of the sample. So a double columnar layer in the middle with good patterns, good grains. Then at the bottom we have this ferritic structure. And here I separate the phases. So the top, this is all austenite. So both of those layers with columns is austenite. Here we have the ferrite. And zooming in on the ferrite, it's martensitic, we have a lot of different orientations in these columns. So if I zoom into that some more, with partitioning, I can select an area inside just one of the ferritic columns, or martensitic columns, I should say. And you can see in the pole figures that there's a very strong orientation distribution in there. So effectively, this means that these are formed from one single prior austenite grain. And these are just 3 different columns, 3 different grains. Then going up, what have we here? Recrystallized equiax grains, large columns, small columns. And this just seems to bump into each other, but here we have some correlation. Now, if I quantify the orientation distribution, at the bottom, I have a very sharp interface. This is this thin columnar layer and the small grain ferrite. I have a very sharp orientation distribution. So that suggests a phase transformation. If I look higher up, this interface, there is no preferred orientation at all. So it's just random with lots of low angle boundaries. Okay, now what can we do? We can apply another function in OIM analysis, the parent grain reconstruction. We can look at the prior austenite grain structure based on what we have. So if I look at this martensitic structure at the bottom, we can run it through the software, calculate the most likely austenite host grain for each lamella, and then this came out. And as you can see now, this lower thin columnar structure is just completely epitaxial with whatever is underneath. You can see the color, you can just trace the colors beautifully from there to there. And the reason why this columnar structure was left over is chemical. So also there, the reason why there we did not have misorientation preference is it's just random, is butting against each other. And here we have a chemical segregation. So we added a little bit more nickel here from during the welding that stabilized the austenite, and here at the bottom the austenite transformed back to martensite. And if we look at that in a little bit more detail, we can see it again. So we have 2 grains with that very distinct distribution, and after the parent grain reconstruction, the orientation fits beautifully as expected inside these circles. Now, finally, the swirls, as I mentioned, we have here the blue area is martensitic, and then we have the austenite around it. And here we have chromium, here we have nickel, and you can see there's some variation in chromium and nickel in there. And when I do a reconstruction, we get those very big grains that correlate with the nickel area up there. But during the mixing, during the plunge of the stud into the melt pool, there was just a little bit of mixing of the ferritic base material with the austenitic material from the stud, and that allowed some grains to remain austenitic and others just transformed back when it was cooled down. So just a sequence of events that I have here. Recrystallize, it doesn't melt. There's the, you can just read through that, but the entire volume solidifies, this double layer of austenite grains forms, but the chemistry causes the lower part to change into a martensitic structure, and that gives you this standalone band of austenite columns. That is just a typical analysis where you can get a material that you may not know, look at it, work through it, and see if you can understand the microstructural evolution. So just to summarize that then, OIM Analysis 9 is a very powerful EBSD software package that gives you microstructural visualization, analysis, quantification for interrogating, understanding your data. It has a lot of tools that you need to understand your samples. It's easy. The quick toolbar for your initial analysis and the right-click sequence for all the customization is just the same. You can learn it very, very quickly to use. The partitioning is there to select specific component of the microstructure, and then you can customize that to extract just the bits of your maps that you need from your samples. You can use template for repeatability, and then you have a reporting capability as well for any of your custom analysis. And when you have stored all the patterns, you can really maximize analysis success rates using this customization of the background, NPAR, and spherical indexing. So it's very, very powerful. And before I forget this, the most important button in the software, I'll put a big arrow on it, right there, help. If you have used the software before, if you don't know how to do something, please look it up. The help is really very good. And inside the help is a section with tutorials. And this will run you through the software, through all the functionality, and will guide you through all the click sequences that you need to do certain analysis. Even if you have used OIM Analysis for a while, please try to find the time to run through these tutorials, because I'm pretty sure you will find new things in there as well. And with that, I would like to thank you for your attention. And if there are any questions, then please. Okay, now let's see. I see some questions. That's a good one. How much time is typically allocated for the microstructure analysis? I guess that really depends on your field of science or where you are located. In a university or a research institute, that it can be that your data acquisition takes half an hour and you're spending 2 weeks for the reprocessing. If you really want to understand a lot of details. When you're working in a facility where you are using EBSD as a quality control tool, you may need to run 20 or 30 samples each day, and you don't have the time to look in detail at each individual data set, and that's what the templates are for. Another question, for good re-indexing, would you recommend saving only the unprocessed images? Not necessarily. I like to see as good as possible indexing result as I can get when I collect the data. And when the pattern are already to a large extent optimized with a background, if I do it again, if I add another sequence of background processing on top of that, I see that the contrast in the pattern gets a lot better, and it allows me a little bit better to correct for any topography that I may have. Normal background processing is for is like an average signal, but if you have topography on your sample, the intensity will shift a little bit, and you will see that. And when you do an average background subtraction during acquisition and do a dynamic subtraction afterwards during reprocessing, you can almost completely hide any topography effects and get optimum indexing everywhere. Okay. How do you remove some areas in your sample that look black during EBSD from analysis during using OIM? I guess that really depends on why they are black. If it is really a part of the structure, if it's a pore, what I would do is do a CI filter, remove the bad points, and then make sure that when I show the IQ map or a CI map and a color map on top, that I use the in the preferences, you can set up the color map as transparent. So you see the grayscale map over the entire field, but only the correctly indexed points in color. I had a few examples like that where we had the full image in grayscale and just the selected bits in color on top. That's the first thing I would do. I'm very reluctant to apply a lot of cleanup, because in most cases misindexing is there for a reason. It can be polishing, it can be a specific orientation that refuses to index, it can be extreme deformation for specific parts, another phase, and if you do cleanup to remove bad points, then you may actually modify your microstructure more than you want. Okay, then another question, is there a good strategy for the parent grain reconstruction to look at the austenite host grains? The main thing is that you need to try to minimize misindexing along grain boundaries, because the reconstruction is based on orientation relationships. So if you have some misindexing along grain boundaries, actually this is the only time when I use cleanup to grow the grains a little bit. The caveat here, be careful, EBSD cleanup I often describe as in situ grain growth experiments in your computer. Be very careful when you do that. But when you know, okay, there's just a few separate pixels along boundaries, you can do a dilation or one of the other cleanup tools to touch the grains together. And that will allow you the best possible reconstruction. So there I would do a little bit of a cleanup. There are multiple phase relationships available. They're predefined in the software, or you can define your own. Just see which one works best for your situation, for the history of your material. Because the calibration, it's pretty quick. Okay, then is there a possibility to script custom functions? At the moment, there is not. There is a possibility to use the batch processor to script exporting the data, getting the analysis that you want to do in a template. So the scripting is like the template setting that we have, but there is no, let's say, Python interface into OIM analysis at this moment. Then There's a few more questions. One, how can you define the distribution of martensite in the microstructure quantitatively? I assume that you mean how to separate the martensite from the ferrite. There are a few things to consider. It's not easy. Sometimes I describe this as the holy grail for EBSD because the EBSD patterns are almost identical. The main difference being that martensite tends to be deformed and ferrite not when you have them together. So you can use the deformation in the martensite that is also visible in the pattern quality. So your EBSD IQ values will be lower in martensitic areas. One trick that you can apply, actually martensite ferrite separation is easier in a tungsten microscope than a field emission microscope. In a field emission microscope, the beam is so thin and the interaction volume so small that even in deformed martensite, you tend to get really good patterns. On a tungsten microscope, the beam is thicker and you will get many more dislocations in the information volume, which means that you will have a much larger contrast between the clean ferrite and the deformed martensite. So you can use the IQ. If you do that, make sure to use the grain average IQ. Otherwise, all your grain boundaries where you have overlapping patterns will be identified as martensite. So don't just use IQ, take the grain average. But then you can do that. I often like to use some form of misorientation measurement in there. That is also quite a nice parameter to tell them apart. Let's see. Another one here is, can we export grain-based grain files and points-based grain files at the same time in a batch? When you can export a grain file that will have the grain identities in there that should fit together with all the other displays where you use a grain ID. I'm not entirely sure if you see something go wrong, but normally that should work, but you need to do it in one go, because if you do a little bit of cleanup or any other reprocessing, the grain assignment might change. Then I see here in all the versions there was a way to measure misorientation of two highlighted points using the average grain orientation. That is also present in OIM 8. You see right here, you can't find it. In the highlighting toolbar, you have a selection where you set up the highlighting parameters, and there you have a checkbox for the average orientation. And in OIM 9, you can do it from the ribbon as well. And then the last one, I think, because time is going on, how fast is spherical indexing compared to HUF? Live HUF indexing, depending on the settings, can run full speed of the camera, 6,500 points a second. Spherical indexing on the computer that I have available here can run at 10,000 points per second for single phase and 5,000–6,000 points per second for dual phase materials, because you have to do it all twice. But that is very strongly dependent on the computer hardware, especially the GPU. The spherical indexing is running almost uniquely on the GPU. So the higher performance card you have there, the faster it will be. Okay. There were a few more questions, but I think I have to stop at this. I will read through all your questions and reply via email. If there are any other questions coming up, feel free to contact me. You see my email there on the page, on the slide, and I will do my best to guide you in the right direction. So again, thank you very much for your attention, and I wish everybody here in Europe a very nice evening, and in the rest of the world, good evening and a good day.